In this video, we're going to be taking a look at a bunch of multiple choice strategies for the AP Physics 1 exam to make sure we understand pacing, thinking process, and how to prepare for the exam properly. And for the second portion of the video, we're going to be taking a look at all the same sorts of strategies and examples with free response questions as well. So the first area you want to be familiar with is the pacing. So I think most people will typically know that there's 50 multiple choice questions, 5 multi-select questions that you have to select more than one answer to get full credit, and we have a total of 90 minutes for the entire exam, which means that we have exactly 1 minute and 48 seconds per question, so slightly under 2 minutes. So what I would do is I would either have a watch on your wrist or make sure you have a clear view of the clock in the class. And then from there, check your progress every 30 minutes so that you're not checking it every 5 minutes or 10 minutes. And that way it's kind of interrupting your focus and your flow of the test. So if you finished about 17 questions every 30 minutes, that means you're right on pace. So if you check every 30 minutes and you are in the neighborhood of 17 questions, that means you're on a pretty good pace. Lastly, for the pacing, don't slow down if you're working at a faster pace. So if you're naturally working at a faster pace and you don't feel rushed and you feel like you're analyzing the questions properly, but you maybe check after the 30-minute point and you're 20 to 25 questions in, that doesn't mean you have to slow down. What I would do is I would continue at that pace. And then if you finish early, then take your time in going back and rechecking some of your work and some questions that were a little bit more difficult. Next is the thinking process. There's a lot of things I have listed under the thinking process. So it's probably going to be a little bit more helpful once I do some examples and then talk you through that thinking process. But let's go ahead and take a look at a few of those things. We have questions that require deep content knowledge. So there pretty much won't be any questions that you read and you think of an answer immediately. Most of them take a little bit more thought and analysis. You want to read the question at least twice. So the first time you read the question is where you kind of get the initial ideas in your head. And the second time you read the question, you're developing a little bit more understanding of it, doing a little bit more labeling as you go. So speaking of labeling, you want to draw and label as much as possible. So if you draw out and label as much as possible, that will trigger more thoughts and different ideas that would otherwise be a little bit more difficult to pull out of your brain as you're just reading the question and not writing more out. Next, while you're doing that, you want to refer to equations for mathematical and conceptual ideas. So oftentimes when people look at equations, they think about that as something to plug in numerical values and find an unknown variable. But a lot of times they're actually showing you the connection between a bunch of variables and relationships for a certain idea. Next, you want to develop your idea and answer choice before reading the answer choices if possible. So if you can read a question and develop an idea that you're looking for in your answer, it's best to develop that idea first before reading the answer choices and then potentially getting thrown off by the different answer choices that are provided to you. Next, use the process of elimination for many or all problems. So your goal is to get as close to a correct answer as you possibly can. So some questions are going to be very difficult. So your best shot is eliminating 1 to 2 answers and then taking your best guess from there. So using the process of elimination for just about every question would be advantageous. And then lastly, after you answer the question, then reread the question. So after you develop a solution and then you circle a specific answer, reread the question and see if it matches up to what you circled for your final answer. As far as preparation goes, make sure you review and study the concepts well in advance using videos, notes, textbooks, lectures, just whatever materials you have. You typically want to do that maybe about a month in advance or even earlier to make sure you have time and you're not rushed and you have time to take a look at all the content before really getting into that practice. Okay, once you get to that practice part, that's where you really need to step it up and spend the majority of your time. Practice is definitely going to be the key. Practice as much as possible in test-like scenarios. So don't just randomly look at questions and then kind of answer them feeling like you're getting a lot of progress done. You want to make sure you have a quiet area, make sure you're timing yourself, and make sure you're taking a bunch of questions that are similar to the AP test and taking the actual official practice AP test questions would definitely be the best. So with all those things in mind, let's go ahead and take a look at a few examples, and I'll go ahead and narrate my thinking process as I go through 3 different multiple choice questions. So as I just mentioned, we want to read the question twice. I'm not going to read it out loud twice during the video, but you want to make sure you read it twice when you actually go through the problem. So I'm just going to go ahead and read number 1 over here on the left. And it says 2 solid spheres of radius r made of the same type of steel are placed in contact as shown in the figures above. The magnitude of the gravitational force that they exert on each other is F1. When 2 other solid spheres of radius 3r made of this steel are placed in contact, what is the magnitude of the gravitational force that they exert on each other? So now as we're going through the question again a second time, we have 2 solid spheres. They have a radius r. It's the same type of steel. They're placed into contact with each other. And then it's focused on gravitational force that is developing this force, which we're calling F1. So I'm going to go ahead and say that this over here develops a force of gravity that we're calling F1. And then we have 2 other spheres of now radius 3r. So I'm going to go ahead and draw a new picture. And I'm trying to develop some ideas, and the ideas that I'm developing in my head as I'm reading it the first couple of times is that it's all focused on the universal law of gravitation. So although you may not feel it's necessary to do this, I would recommend writing out the entire formula so you can see all the ideas right in front of you, and plus it only takes a couple seconds. Now with my new scenario, I'm thinking about how the mass and the radius, which is the separation distance, might be affected in our new scenario. Now, when we're measuring the separation distance, we're measuring the separation distance from the center of mass. So this is actually a distance of 2r, and this is a distance of 6r. So that's the first thing. Secondly, obviously the mass is going to be bigger with 3 times the radius, and we said that they're 2 solid spheres. So since these aren't 2-dimensional objects, they're 3-dimensional, a sphere is 4/3 pi r cubed when you're taking a look at its volume. So if we're tripling the r, basically we're getting rid of this r and then we're replacing it with a 3r. And if you do 3r cubed, once it comes out of that cubed value, it's going to be 27r cubed. Now that's going to happen with the first mass and the second one as well. So when we take a look at that conceptually, that 3r is going to change our radius by a factor of 3, but it's going to change my volume by a factor of 27. So that means I'm going to have 27 times more mass for the first one and 27 times more mass for the second one. Now, as far as the separation distance goes, we went from 2r to 6r, which is 3 times the radius. So if we're tripling this radius, it's going to be 3r squared, which is going to come out as 9r squared once the entire value is squared. So if we go ahead and we take 27 times 27 and we divide it by 9, we get exactly 81. Okay, and then 81 is one of our choices over here. So that is a fairly difficult question. There's a bunch of different things going on. If I were to initially look at it, I would guess that it's very probable if I have 2 spheres that are significantly larger, we would not have the exact same force of gravity of F1 that we initially had. And then from there, I would say B, C, and D are possibilities. So from there, you're going to work in a little bit more detail as we did over here, and then figure out how many times greater it is. Okay, I'm going to reread the question one more time. And then as I reread it, I want to make sure that all of my ideas follow up with what I did. Did I use some ideas that they're spheres? Did I use some ideas that they have a radius r? Then finally, I'm going to reread the question one more time and make sure all my ideas match up. And as I reread the question, I noticed that they are spheres. It originally had a radius r. They were in contact with each other. It started with F1. And then we have now 2 spheres that have a radius of 3r. They're still in contact. So it looks like all the ideas that I put into place were accurate with what the question asked. Now moving on to the next question. As I said, we're going to want to read the question twice, but I'm just going to read it once out loud. While traveling in an elliptical orbit around the sun, Mars gains speed during the part of the orbit where it is getting closer to the sun. Which of the following can be used to explain this gain in speed? So we have an elliptical orbit, the Sun, and Mars. And based on what I know about universal gravitation, we have a force of gravity on Mars by the Sun and an equal and opposite force on the Sun by Mars. And that force of gravity is the centripetal force that causes it to change direction and go in that elliptical orbit. Now, the key to this question is really paying attention to specifically what they are asking for. So they're saying that it's getting closer to the Sun, and then we're using this idea, what is used to explain this gain in speed. So before I start reading my answer choices, I'm going to develop some of the ideas that I know and see if any of the answer choices matches up with them. So when Mars is over here, it's going to have a greater gravitational force slash centripetal force. And because it's closer, it has that greater force because of this formula over here, which I just recently analyzed. And that would make it seem like it's going to be the contributing factor in causing it to gain speed. So that's my initial idea, and I'm going to go ahead and read through my answer choices and see if anything matches up pretty closely with that. So A, as Mars gets closer to the Sun-Mars system loses potential energy and Mars gains kinetic energy. That's an idea that I'm pretty familiar with, is that as potential energy is lost, kinetic is gained to maintain that conservation of energy. So far, A sounds like a pretty good option. For B, a component of the gravitational force exerted on Mars is perpendicular to the direction of motion, causing acceleration and hence a gain in speed along that direction. So for B, we have the object having a certain velocity or direction, and we have that gravitational force, which seems to be all perpendicular. So as far as a component, that doesn't really sound like something I'm too familiar with. So as of now, I don't really like the answer B. So I'm going to go ahead and cross that one out. For C, the torque exerted on Mars by the Sun during the segment of the orbit increases the Mars-Sun system's angular momentum. So for the entire system, the angular momentum is going to be conserved unless some kind of external force acts on it. So that doesn't really sound like an answer that I like either. And then D, the centripetal force exerted on Mars is greater than the gravitational force during this segment of the orbit, causing Mars to gain speed as it gets closer to the Sun. The centripetal force and the gravitational force are the same thing. So that doesn't really sound like a good answer choice either. So I'm going to go with choice A, which does end up being the correct answer. Now, when we did this first example problem over here, now I went through it slowly because I was just slowly talking through the steps, but my best estimate is for that question, it would have taken me more than the 1 minute and 48 seconds. I would say it would take me roughly 3 minutes to solve that question because that one was a little bit more in depth. Now, when you have questions like that, I would be conscious that you're taking more time on them, but also not to get overly frustrated or rushed by them. Because now, when I did number 4, if I were to do that question in real time, that question probably would have taken about a minute, possibly under a minute. So for number 4 and number 1 combined, their total time would have been roughly 4 minutes total, which is on pace. So overall, I would be on pace for those two. So you want to keep that in mind, that the style of the questions are different. Some of them take a deeper analysis and some of them are fairly quick. So you want to make sure you have a good balance of those. Now moving on to this question, which is question number 5. It says the graphs above represent the position x, velocity v, and acceleration a as a function of time t for a marble moving in one dimension. Which of the following could describe the motion of the marble? Now, although I'm tempted to read the answer choices, I'm going to stop myself and I'm going to focus on the graphs. Now, all the graphs are translating the same type of motion. So what I'm going to do is I'm going to look at the graph that I feel most comfortable with and then take a look at that graph. I know the acceleration graph shows the least amount of information. It just shows that there's a positive acceleration. So I'm definitely not going to look at the acceleration graph very much. So the position and velocity graph are basically showing the same sort of thing in different ways, but I think I'm a little bit more comfortable taking a look at the velocity graph. So I'm going to go ahead and do that. So we have this first segment down here that is below the x-axis. So I know this is going in the negative direction. And then I also know because it's going towards 0, it's slowing down. And then for the second part, it goes up above the x-axis, so that's in the positive direction. And it's rising and moving away from 0, so I know it's speeding up. All right, so with those ideas in mind, I want to make sure that my answer choice matches up with those ideas that I initially thought about, and if they don't, I'm going to immediately cross them out. So A says rolling along a floor and then bouncing off a wall. So rolling out along the floor sounds like constant velocity to me, so I'm definitely going to cross that one out because we have all accelerated motion. B says rolling down one side of the bowl and then rolling up the other side. If it's rolling down, that means it's speeding up. Okay, already I'm going to cross that one out because initially we have something that's slowing down. For C says rolling up a ramp and then rolling back down. Okay, so if it's rolling up a ramp, it could be going in the positive or negative direction, depending on which way the marble is going. Is it going left or right? But if it's going up a ramp, it's definitely slowing down. And then if it's rolling back down, then it's speeding up. Okay, so that so far sounds like something that I do like. I'm going to hold off on circling that answer. And then D says falling and then bouncing elastically off the floor. Falling would mean that the gravity is pulling it and causing it to speed up. Again, the first half of my motion is showing something that's slowing down. So I'm already done with choice D. That's not correct. So I'm definitely going with choice C. And then typically I would reread the question at the end, but because it's mostly based on the graphs and matching up the graphical motion with the answer choices, I'm pretty confident in my choice C, and then I'm all done with problem number 5. Now let's go ahead and take a look at free response strategies for the AP Physics 1 exam. Now, the overall approach strategy that you definitely want to implement is this. So first of all, just kind of knowing what the test looks like obviously is important. You have 5 free response questions. These are the different 5 types that you're going to see right over here. And you want to skim all 5 questions and you want to use your intuition to rank them easiest to hardest. If you have the ability to, I would say it would be good to label them 1 through 5, 1 being the easiest and 5 being the hardest. And after spending a little bit of time to skim, if you can rank them, then you'll know to start with, what you ranked 1, then 2, then 3, and then so on. Now, that in itself is going to be sort of hard because you're going to be comparing, is this question harder than the other one? Is this a 2 or is this a 3 or is this a 5? So my suggestion is using this right here, labeling stuff as E, M, and H, easy, medium, and hard. And then that way you know how to start with the E's, go to the M's, and then finish with the H's. That way you don't have to spend as much time doing this ranking system of 1 through 5. If you can quickly do that ranking system 1 through 5 and you know that you've been effective doing that with practice tests, then by all means definitely rank them 1 through 5. I think for the majority of people, the EMH system is going to work a little bit better. So that you could probably efficiently label stuff as E, M, and H in the matter of like a minute or two. So if you're spending more than a minute or two, I would say 2 might even be a little bit on the long end. But you want to spend as little as time possible so that you can use time to answer your questions as accurately as possible. So that's the first thing that you definitely want to implement no matter what level you're at. Now, some additional strategies, be aware of the suggested times. If they give you a suggested time of 7 minutes, just kind of keep that in the front of your mind. Identify the specific task for each question and then circle the verb. So some might ask you to calculate a specific value. Some may ask for an explanation. So make sure you keep that verb in the front of your mind as you're answering that question. And as I said, probably just circle it and make sure you can identify what they're asking for. Practice your organization and show all work, include all major concepts that you need to apply. Okay, so for example, if you're looking at a question and you might be using the conservation of energy, then maybe just writing some notes about the system or a question uses the conservation of energy might already earn you a point without a whole lot of thought. So for me, organization doesn't come very naturally. For some of you, it does. So you kind of have to know yourself by analyzing and reflecting on your own work. If you are not that organized, you definitely want to make sure you're not scribbling work all over the place, but writing it down in an organized manner so that you and the graders are able to follow your work easily. Next, if you put down incorrect work, then put an X through it instead of erasing it all. So if you find yourself writing some things that you change your mind about or you're sort of headed towards the the wrong solution, then go ahead and just put an X through it and then keep on moving on. If you find a certain sub question is particularly difficult or you are short on time, then skip to the next question. So maybe you go to part A and part A is pretty tough. That doesn't mean you can't do part B and C. So they're all related to the main question, but they're not all intertwined so closely that if you can't do A, then you definitely can't do B and C and so on. You might in fact find ones that are easier later in the question. So you definitely want to make sure you kind of skim through those and do the ones that you're able to do. Finally, make sure you study and practice each type of question and be familiar with the scoring. So you don't want to just be taking a bunch of free response questions and then feel like you're getting the practice that's necessary. Because if you're doing all short answer questions, then you're not really being exposed to all the different types of questions. So you want to make sure you're getting a good variety of all the different types of questions. And then secondly, you can go ahead and Google search AP Physics 1 free response question scoring and then see how the questions are scored, because then that way you can figure out what things to write or what things to focus on to get as many points as possible. Okay, so let's go ahead and do a couple of these free response questions. Now I'm about to work out a short answer paragraph argument. I would have already skimmed through all of the problems, and this would look like a E type question. So E for easy, M for medium, H for hard. So I want to definitely take care of this one first to get the most amount of points possible. If I were to do the ranking system, this would have been my number one, as in my easiest question that I want to start with. So let's go ahead and get started. It says we have a suggested time of 13 minutes. So I'm going to make sure I kind of keep that in mind as I'm going, but I'm not going to check the clock every couple minutes, but just make sure I kind of stay on pace of what I think 13 minutes is. And if I'm doing good, just kind of keep on moving along. A student has a piece of clay and a rubber sphere. Both have the same mass m, and both objects are thrown horizontally at the same speed at identical blocks that are rest at the edge of an identical table as shown. Where friction between the blocks and the table is negligible, after the collision, both blocks fall to the floor. In case A, clay sticks to block A after the collision. In case B, the rubber sphere bounces off of block B after the collision. So both of these have a mass m. Both of these have the same speed, so we'll call that v. And then both of these blocks are at rest. So the first thought I have in my head is if we have two things that have the same exact mass and velocity, then they have the same exact momentum, and the two things that are at rest clearly have the same momentum also, which is 0. So the total momentum of each system is going to be the same. So that's what's running through my head so far, and I'm going to see how that applies to the questions that I'm going to be asked. So I'm going to go over to part A, and I'm going to take a look at these diagrams. First, it says case A, the momentum of the clay block system immediately after the collision. Case B, the momentum of the sphere block system immediately after the collision. Now, in my head, I already had an idea that the momentum before each of the collisions was the same. So because momentum is conserved, the momentum of the sphere block system after the collision should be exactly the same for both. So in my head, I'm already thinking that this vector is going to be exactly the same as the vector I draw over here, but I'm going to go ahead and read the question and make sure that is what they're asking. In the figure at the left above, the arrow represents the momentum immediately after the collision for the clay block system in case A. In the figure at right above, draw an arrow starting on the dot, represent the momentum of the sphere block system immediately after the collision in case B. If the momentum is 0, write 0 next to the dot. The momentum, if it is not 0, must be represented by an arrow starting on and pointing away from the dot. The length of the vector should reflect the magnitude of momentum relative to case A. So that does seem to ask exactly what I thought it was going to. And in addition to that, I'm going to make myself a little note that the momentum is conserved. Okay, and that little note is, I guess, actually not for me, but for the person scoring the test, because that is a major idea that I would have to have in my brain in order to apply this vector on the grid appropriately. and any idea that is contributing to the solution. I want to make sure I write that down so I can get every point possible. So that's pretty much it for A. I'm completely done with that question. I'm going to go ahead and move to step B. Step B says after the clay and block A collide, block A lands a horizontal distance dA from the edge of the table. Does the block B land on the floor at a horizontal distance from the edge of the table that is greater than, less than, or equal to dA? In a clear, coherent paragraph length response that may also contain equations or drawings, explain your reasoning. Neglect any frictional effects due to the table or air resistance. Okay, so there's two things I want to accomplish. I want to tell them, is it greater, less than, or equal to dA? I want a paragraph length response that may also contain these couple things. And my one of the main task verbs there is explain your reasoning. So not just tell them what's happening, but also have the physics behind it in your explanation. All right, so I'm just going to delete question A so that I can have a little bit more room to work. So since they gave me the option to have equations or drawings, what I'm going to do is I'm probably going to head that direction first and draw out everything and write equations as well, and then add my response underneath it. That way it's going to help me kind of work through the concepts and sort of visualize them a little bit better, and then also give the graders something to visualize as well. So we have the table for block A, where the block and the clay stick together and they move a certain distance, which they call dA. And it has a certain velocity, and we'll call that VA. So I want to make as many markings and specific variables as I can to keep track of things, and also for the graders to be able to keep track of my work as well. And then I have the second scenario, which is block B. And in my head, I have an idea of what's going on already. So we have the momentum of the clay, and then it's basically picking up some additional mass, which would be block A, and then its velocity is going to drop, and then they're going to move down and fall as sort of one of those projectile cliff problems. For the second one, it's going to head back and sort of have a negative velocity. Now, I know that if momentum is conserved, and in the end they have the same amount of positive momentum before and after the collision, then this would have to have a larger velocity so that momentum would be conserved. So it would go a little bit farther, and we'll call that dB. Now I want to make sure everything is clear. So I did make it look farther, but I'm also going to write down dB is greater than dA. And then over here we got a VB, and then I'm going to go ahead and show them that my VB is greater than my VA. Okay, and then I've already assumed this in my head, but I can't assume that anyone knows what I'm thinking. So I was also thinking that the velocity is the only contributing factor because they're falling off of the same desk. It said identical tables. So because they have the same delta y, that means they have the same time, and then I'll just say falling. All right, so I didn't physically write out a ton of work, but every idea that was in my mind that is contributing to my solution, I want to write down, and things that I normally wouldn't write down, I just want to pour all those ideas on the paper within reason. All of these things are big contributing factors to how I get my solution. So the part that I want to show the graders is why this velocity is greater. And I'm thinking about using some equations. So I'm probably going to add some equations first and then put in the text at the very end. So now I just wrote everything in variable form to try to prove that VB was greater than VA. So I had the MV of the clay initially equals both of the masses combined with one combined velocity, which is VA. So I just did a little bit of algebra there, and then there is my final expression for VA. And then for the second scenario, we started off with the same MV, but we have a negative MVF over here, and we can go ahead and label this VF to stay consistent with these two variables over here. And then we have the mass of the block B with its VB. So then I just did the algebra for that part, and then I have this final velocity for VB. Now I'm not gonna write out all of the sentences, but I've done enough with my drawing and my equations to prove what I want to prove. So I'm going to use words to show that if I take this MV and divide it by the sum of the masses here, that is for sure going to be less than the MV plus an additional momentum divided by a smaller number. So mathematically, this one has to be larger. Therefore, if this number is larger, that means our VB is a greater velocity, hence causing a greater dB because its horizontal velocity is larger if both of them experience the same time falling. Now, let me go ahead and grade my work and see how I did. So the first point is making sure that this is the same length as this. So that is my first point. And the second one is for indicating that momentum is conserved. So I did actually get a point just for this. Okay, so either just writing the words momentum is conserved may have just given you the point right there, or in the bottom here, you may have written that in your explanation. But anyways, it's better to be safe than sorry and go ahead and write your big ideas down first. For the third point, to get awarded the third point, showing why a greater amount of momentum is transferred by the rubber sphere and why the block in case B has a greater momentum than in case A. That would have been in my paragraph length response discussing this. So we'll say that yes, I would have gotten the point for the third one. For the fourth one, it says indicating that a larger momentum leads to a greater speed. That also would have been all tied into my explanation after doing all my drawings. And then for indicating the blocks fall for the same amount of time. So just for putting this little note over here, I did get that point. For point number 6, indicating that a block moving at a faster speed lands at a greater distance, that would have been shown over here in the picture, and then additionally with my words as well. So check to point number 6. And for logical, relevant, and internally consistent argument that addresses the required argument or question asked and follows the guidelines described in the published requirements for the paragraph length response. So I did show equations and drawings as they asked, because I said they said it could contain this. And then I made a paragraph length response afterwards, and I explained my reasoning for everything I was thinking above with my drawings and my equations. So for number 7, check. Now, this was my level 1 question or my E question. So I'm banking on trying to get most or all of those points for my easy ones. And then obviously that amount of points would decrease as I went to my like medium and hard questions. Now, if you're looking at my screen right now, if you didn't know all of those physics ideas, I would say a majority of people would be able to grab a decent amount of points if they're using the right strategy. So if you would have figured out the momentum is conserved, you would have gotten this point over here, drawing the vector. Just by writing momentum is conserved, you would have got the second point. If you went through this problem over here and you maybe did some of those drawings and you showed a couple of these things, like maybe the velocity is greater or the delta y is the same so that you got the same amount of time, you could have racked up maybe 4 points and had a pretty bad explanation over here. But getting 4 out of 7 points is pretty decent if you didn't have a lot of that content knowledge. Now, after I've completed this question during the test, I completed it in its entirety. If I left anything blank, I would make sure I circle it so I can draw my attention back to it later on. Also, the other thing I'm going to pay attention to is the 13 minutes. Take a quick glance at the clock, see if I'm a little over or under. So if I'm a little over or under, I'll just kind of keep a mental note of the pace that I need to keep up. Again, you want to make sure you stay calm. If that took me 15 or 16 minutes, that doesn't mean I need to like scribble stuff in for the rest of my questions. You want to make sure you're still getting the most amount of points possible for the following questions. So rushing through them and not being thorough is probably not the right strategy. But make sure you strategically keep your pace up, but make sure you have a deep analysis of all the questions as well. So let's go ahead and move on and try an experimental design. Now let's take a look at an experimental design question. This question was 12 points and has a suggested time of 25 minutes. So 25 minutes is a fairly generous amount of time, but because there's a lot of reading and you have to write out a procedure, this is definitely going to be quite time consuming. So if I'm just kind of looking at the first part where I have to read what the whole setup looks like, and I have to like design some kind of experiment, and I have this table and procedure I need to write out, I'm going to guess that's going to take at least about 10 minutes for that section. I have a part B, C, and then D. It looks like all of those parts are going to be slightly less time consuming. So I'm probably going to just break up the remainder of my time with those last three subsections. So as I get to this question, this would be something like a medium level question, or maybe ranked like around a 3 if I were to use the 1 through 5 system. So it looks like there's a decent amount of points I could probably rack up here with 12 points total. I'm just going to roughly keep in mind that I'm going to use about 10 minutes for this first section, and I'm going to break up the last 15 minutes for the other sections. So let's go ahead and read what we got here. We have a wheel that's mounted on a horizontal axle. A light string is attached to the wheel's rim and wrapped around it several times, and a block is attached to a free end of a string as shown in the figure. When the block is released from rest and begins to fall, the wheel begins to rotate with negligible friction. Two students are discussing how different forms of energy change as the block falls. One student says the kinetic energy of the block increases as it falls. The second student says that it is because gravitational potential energy is converted to kinetic energy. The students decide to test whether the decrease in gravitational potential energy is equal to the block's increase, the block's kinetic energy from when the block starts moving to immediately before it reaches the ground. So does my decrease in gravitational potential energy equal my increase in the kinetic energy? I'm just going to go ahead and make myself a little note there so I can focus on what the two students are discussing. Part A says design. So we have an important task verb there, an experimental procedure that the students could use to compare the increase in the block's translational kinetic energy with the decrease in the gravitational potential energy of the block Earth system as the block falls, which is basically what I labeled over here already. In the table, list the quantities that would be measured in your experiment, define a symbol to represent each quantity, and list the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you may add them to the space just below the table. In the space to the right of the table, describe the overall procedure. Provide enough detail so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. Okay, so we want detail for another student. We want to reduce experimental uncertainty. And then we can include a diagram, which sounds like something I would most likely want to do, of the setup with your procedure. Okay, so I'm thinking of gravitational potential energy, which is mass times g 9.8 times the height, and then kinetic energy, which is 1/2 v squared. So in my mind, I already have g, which is 9.8. So I need ways to experimentally get mass, height, and velocity. So mass seems like it's a pretty easy one to get. That we were going to use a balance. And I don't know how picky the graders are, but it's not a scale for the mass. It's called a balance. Secondly, we want the height. So let's go ahead and call that h, and then we can use a meter stick for that. And then for the velocity, So as I'm thinking about velocity, because I'm imagining the block is going to be accelerating as it falls, the velocity is constantly changing. So we could probably use some different formulas, but I want the best way to get my final velocity, because we know that our initial velocity is 0. And I would probably use a motion detector for that one. So I'm going to say velocity V, and then the motion detector for that. Okay, that seems like about all I need, because I can get the mass, I can get the height, and I can get the velocity. So then I could just mathematically get my gravitational potential energy and my kinetic energy and compare those. Okay, so for the procedure, I'm just going to go ahead and switch screens so I have a little bit more space. For my procedure, I spent about 5 minutes writing out this procedure. So I just sketched the picture, and I wanted the motion detector to be facing upwards towards this block so it could get a reading of its position, velocity, and acceleration, although I'm just mostly concerned with the velocity. So I want to make sure I get my mass, height, and velocity to plug into my gravitational potential energy formula and my kinetic energy formula. So find the mass using the balance, measure height from the bottom of the block to the motion detector, press collect, and stop the mass right before hitting the detector. Number 4, find the VF, the final velocity, by using the velocity versus time graph. And number 5, repeat steps 2 to 4 with additional heights. Now, one of my main tips for this section, which might sound a little strange, is I want you to visualize yourself in the lab conducting the actual lab. Because now when you're looking at a picture of an experiment that you've never done before, it's hard to imagine all the steps you would do. Now, if you're physically given all the equipment and you're actually working with it with your group and setting them up with your hands, you're going to have a much better idea of how to set everything up and how to measure everything. So I want you to visualize in your head, what would you be doing? What things would you be touching and dropping and calculating and measuring? And when I did that, I thought that I would make a little note here, and I want to release the mass by holding and releasing the wheel, because I wouldn't want to hold the mass over here, because then the string might get a little bit loose and we want it to be taut. So I'd probably hold the wheel here and then release it. And then secondly, I'm thinking of getting the VF on the graph. What I would do is I would locate the maximum velocity before reaching the bottom. Okay, and then I would go ahead and record that, and then I would repeat steps 2 to 4 with additional heights. So now what I'm going to do is I'm going to go ahead and grade my first section, and then I'm going to move to sections B, C, and D afterwards. So for the first point, I was supposed to list relevant equipment that matches the measured quantities of mass, height, and velocity. So it looks like I did do that. So I got 1 point for those things. For listing measurements of quantities sufficient to determine the kinetic energy of the block, I did get the mass and the velocity to get that. So second point, check. 3, for listing measurements of quantities sufficient to determine the gravitational potential energy. I did get the mass and the height, so check. 4, for a plausible procedure, one that can be done in a typical high school lab. So this does sound like things that would be in the typical high school lab. So number 4, even if you came up with a lab that wasn't specifically one that was great for getting kinetic energy and gravitational potential, if you even had a plausible procedure, you would get a point for that. And the final one, for attempting to reduce uncertainty. Now, if I'm looking at my procedure, I'm trying to see if there's anything to reduce uncertainty. Now, I have things to try to be a little bit more accurate, which is this part over here, holding the mass from by releasing the wheel and doing a bunch of extra data points. I don't know if I was attempted to reduce uncertainty enough in order to get that point. So I'd say for point number 5, I maybe didn't get that point. So to reduce uncertainty, I would say do something like take some averages would be a way to reduce uncertainty. just to maybe do separate trials of the same thing and then take averages of them would be a way to get some more accurate data. Now, those are all the points that are rewarded for the procedural part of the experimental design lab. So let's go ahead and take a look at sections B, C, and D now. All right, for section B, explain how the student could determine the kinetic energy of the block immediately before it reaches the floor using the quantities you indicated in the table in part A. So we basically want how are we going to get the mass and the final velocity. And we want to determine the kinetic energy of the block immediately before it reaches the floor. So we can go ahead and use the mass from our balance. And then for the velocity, again, I'm visualizing what would happen with the lab. And it seems like it would probably be accelerating, but not quite accelerating at negative 9.8 meters per second squared. So I would probably look at my velocity time graph, probably see some kind of rise. And then as it contacts the bottom, it would probably just kind of be all over the place. So this velocity over here. So I would say locate the maximum velocity before hitting the detector. And that would give me my VF, and then use 1/2 mv squared. And we'll say V final squared. Okay, that sounds sufficient enough to get the mass and the velocity and then plug it in. Okay, let's go ahead and take a look at part C. The graph above represents both the change in gravitational potential energy of the block wheel Earth system and the translational kinetic energy gained by the block as functions of the block's falling distance d. On the graph, draw a line or curve to represent the rotational kinetic energy of the wheel as a function of the block's falling distance d. Okay, so here is my main task verb, draw a line or curve to represent the rotational kinetic energy. Now, if I'm looking at my graph, we have a kinetic energy, a rise in kinetic energy that is a little bit above 0.1, and then we have a dotted change in gravitational potential energy, which is negative because it's losing, that is negative 0.4. So the total net loss of the entire system is around negative 0.3, and the energy should be conserved. So I'm just going to write down energy is conserved in the system. And then I'm just hoping that if I get this question wrong, then maybe I'll get a point that way. So if I want it to be conserved, then it looks like if this is a pretty solid point over here where it's at 0.1 and this one is at negative 0.3. So I want this to be about at 0.2 and this one to be slightly above 0.2. And then I'm going to draw a line that sort of matches up with those. So then if you add the two positive components at 15 at least, you can see it pretty clearly at 0.1 and 0.2, that equals positive 0.3, and this is negative 0.3. So then energy would be conserved with a net gain or loss of 0. So that looks pretty good to me. So I'm going to go ahead and move on. It doesn't look like there's too much I need to double check there. All right, for part D, it says the students also measure the angular velocity omega of the wheel as the block falls and determine the rotational kinetic energy Kr of the wheel. The students then make a graph of Kr as a function of omega squared as shown on the graph above. Draw a straight line that best represents the data. So our task is to draw a straight line. Using the line you drew for part D, I calculate an experimental value for the rotational inertia of the wheel. Okay, that sounds sort of tough, so I'm going to hang on to that and maybe just draw my line. So I'm going to draw a best fit line, and it looks like it's going up a little bit and then sort of flattening out. So I'd say about on average, it should be maybe something like that. Okay, now I cheated and I used the function on my computer to make a perfectly straight line, but make sure you use a straight edge, and then you find the average location of where the dots are falling, and then put your best curve in there. Now, using the line you drew in part DI, calculate an experimental value for the rotational inertia of the wheel. Now, it's plotting kinetic energy and omega squared. Now, those don't really seem like things that are normally plotted with each other. And if I look at my formula sheet, I see that there's a formula 1/2 I omega squared. And that's just about the only place I've ever seen K and omega squared together. I'm sure it pops up in other places, but as far as typical places you might see it, that's the only place I'd possibly see it. Now, when you're looking at a graph, basically what you should be thinking about is, what am I going to get with the slope? What am I going to get with the area? Okay, it's probably not as easy as just looking at a direct data point, so I'd think of slopes and areas. So slopes, you're dividing change in y by change in x. The area, you are multiplying your change in y by your change in x. Okay, so we would either want these two things multiplied by each other or divided by each other. Now, they asked me for the rotational inertia. So I'm going to go ahead and solve for the rotational inertia mathematically and then see what happens there. So I'd multiply both sides by 2 and then divide both sides by omega squared. And my I equals 2 kr divided by omega squared. Okay, so my y value is the kr and my x values are the omega squared. So the slope would be this right here. So if I just take 2 times my slope, then that should give me my answer. So let me go ahead and see if that works. So I'm going to put 2 times, and I like to take the very last point. Sometimes people like to find a point that hits one of their lines, but let's just go ahead and say that the change in y is 1.2 minus, and it looks like roughly 0.1. That's not quite perfect. And then the change in x, it looks like it's about maybe 37. And then my initial x point is 0. So if I take 1.2 minus 0.1, it's 1.1 divided by 37, which gives me about 0.02973. Multiply that by 2, and then that gives me 0.59. So I'm trying to think of the unit for I right now, and I'm kind of blanking out. So I'm just going to leave it blank and just hope that's going to be good enough getting the value there. All right, so let's go ahead and grade this section for section B. 1 point for indicating that mass and velocity are needed. So it looks like I got that right over here. So this is my 6th point overall. And even if you had no idea how to do that, if you just expressed that you needed mass and velocity, then you would have actually gotten a point. So never underestimate the little bit of information you might have in your head. And then you get a 2nd point for a valid explanation of how the final kinetic energy could be determined. I think mine is fairly valid. So we'll just go ahead and say I got the point for that one. For part C, we're drawing a straight line that passes through the origin and has a positive slope. So even if this line didn't match up exactly where it's supposed to be numerically, if I just drew a straight line that passes through the origin with a positive slope, I would have already gotten a nice little point there without trying too hard. And then the 9th point, it says for drawing a line that yields a total energy sum of 0 at all values of D. So it looks like I did pay attention to that. So for the 9th point, I did get that one. All right, for my final couple points, it says for correctly calculating a value for the slope using points in the line drawn, or a statement that a calculator was used to do a linear regression. So it looks like I did find a slope over here, and whether it was correct or not, I did have some work showing that I was finding a slope, which does matter. And the final point is for both of the following: correctly relating the slope of the graph to rotational inertia and a value of rotational inertia consistent with the calculated slope with correct units. So I didn't have the units because I blanked, and that should have been in kilograms meters squared. So I needed to do a bunch of things: correctly relating the slope of the graph to the rotational inertia, which is basically this part over here, 2 times the slope, and then also having a value of rotational inertia consistent with the calculated slope with correct units. So all of that being said, I didn't get the point for the very last one. Now I actually skipped the 11th point. It said for drawing a reasonable best fit line. So this is reasonable, and it is a best fit line. So let's go ahead and say that I did get that point. Okay, so making sure when you do these long problems to really pace yourself. If you're given 25 minutes, kind of sectioning off a certain amount of time for the procedure and the following questions is going to be pretty smart. And then remember, if you just label things such as this, that you're looking for mass and velocity, for simple things like that, you're going to get a point. For drawing a best fit line that makes any kind of reasonable sense, you get a point for that. So just don't underestimate any idea that you have in your head, and go ahead and put that down on the paper, and then hopefully you get as many points as possible. So I hope that was helpful in helping you out with multiple choice and free response strategies and narrating some of the problems. So good luck on the AP Physics 1 exam. Thank you.